So one of the things you might say is, Dr. FeS, why the heck are we doing this H2S stuff when all we need to look at is, in this case, the example that we're going to look at is iron sulfide in solution. The reason for this is if we look at our experimental conditions, right? Experimentally, our concentration of H2S is going to be 0.1 molar. Our concentration of our metal 2 plus is roughly about 0.01 molar. And our concentration of HNO3, because we add nitric acid to this solution, which since nitric acid is a strong acid, that's going to be equal to the concentration of H plus, and this equals 0.3 molar. So here's experimentally what we have in our particular test tube. You're heating this stuff up. There looks like there's some black solid forming. Something's going on here. Depending what separation we're in, what is actually happening at the pH levels that we're looking at? So the first question that we want to answer is, under these conditions, will FeS, or iron sulfide, precipitate? And whether or not this precipitation will form will dictate whether or not this cation is in group 2 or if the cation is in group 3. So we have to think about what's going on in solution. Our first thing that we look at is if we have iron sulfide as a solid, it's going to form an equilibrium with iron 2 plus in solution plus S2 minus in solution. So here's our first expression, and everything would be great, but this sulfide ion, which stinks incredibly and has an awful odor, not only makes it a pain to work with in that regard, but also the S2 minus ion in solution interacts with water to form an equilibrium with HS minus plus OH minus. So we now have two equilibrium expressions that we have to deal with. If we have two simultaneous equilibria, we can add them together. The S2 minus is present on both sides of the equation, so our overall equilibrium we see is FeS as a solid plus water will be in equilibrium with Fe2 plus in aqueous solution plus HS minus in aqueous solution plus OH minus in aqueous solution. Typically, you'll see a KSP value written for this entire overall reaction. And for iron sulfide, our KSP is going to be 6 times 10 to the minus 19. So if you look on some of the KSP tables, sometimes you'll see a little star for, FeS or MNS or bismuth sulfide. Any of these types of sulfides, the KSP value that's going to be written is for this entire equation right here, where we take, instead of Fe, it can be any metal cation that we have in our solution. So keep that in mind when you're looking at the KSP tables, and it's going to be for this particular equation. What we have to do is compare Q versus K. So if we are going to write a Q expression for this overall reaction, Q is going to be our iron 2 plus concentration times the HS minus ion concentration times the OH minus concentration. So we have to, for iron sulfide, compare this product right here to the KSP, which is 6 times 10 to the minus 19. If Q is greater than K, we'll have a precipitate form. If it's less than K, that precipitate will not form. So we have a little bit of math that we have to do. And the first thing that we need to look at is the HS minus concentration. The HS minus concentration comes all the way up here from this particular expression. So if we were solving for our HS minus concentration, our concentration of HS minus is going to equal 9.5 times 10 to the minus 8 times the concentration of H2S divided by the concentration of H+. One thing that I will point out, this HS minus concentration is dependent upon the H plus ion concentration. So this HS minus concentration can be manipulated by changing the pH. Remember, this is very important when we're separating these things out based on pH. So if we wanted to set up this expression here, our Q is going to equal the iron 2 plus concentration, which is given in this case to be 0.01. The HS minus concentration is going to be 9.5 times 10 to the minus 8 times the concentration of H2S, which in this case is 0.1, divided by the H plus concentration. In this case, we're using 0.3 molar nitric acid. Nitric acid is a strong acid, so this is going to be 0.3 molar for the concentration of our H plus. The concentration of the OH minus can be determined using the Kw. Remember that the concentration of H plus times the concentration of OH minus is going to equal Kw, which is equal to 1 times 10 to the minus 14. So for our OH minus concentration, we can plug in the value of 1 times 10 to the minus 14 divided by 0.3. If we multiply all of this out to get a value for Q, our Q is going to equal 9 times 10 to the minus 24. I said previously in this particular example that the KSP, which equals 6 times 10 to the minus 19, is going to be greater than the Q. So the conclusion that we can make is, therefore, no precipitate will form. And as this conclusion, or a part of this conclusion, is we can say that since no precipitate will form, iron 2 plus is included in group 3. So our iron 2 plus is going to be included in our group 3, characteristics, or we'll place it in that group. And remember, we are grouping these metal cations based on their solubility characteristics. That's what we said way back in the beginning when we were looking at these solubility rules, okay, and why we group these particular ions the way that we do.